did you become one of the most influential scientists in Perovskite solar cell research, and what have been the most notable achievements to date?
So Perovskite solar cells are simply solar cells containing metal halide perovskites. So I first became aware of metal halide perovskites in 2009 when visiting some colleagues and collaborators in Japan. So the first paper using metal halide perovskites in solar cells had just published, and this was from the group of Tom Miyasaka in Towan University. And Tom gave a presentation and presented this work, and it was very impressive. The most impressive aspect of it was that he just took two salts, lead bromide and methyl ammonium bromide, put them together in a solvent and spin coated a film, and it crystallized immediately during spin coating and formed a material. At the same time, back in Oxford, I'd been playing around with quantum dots, lead sulfide nanoparticles, and they were an extremely tedious synthesis process, and it took a long time, weeks, in fact, of work to make devices, whereas this perovskite material appeared to just form instantly. So that was something that I found quite interesting. I subsequently returned to the UK and managed to get a collaborative grant with one of my colleagues, Taku Murakami, and I sent a PhD student back to Japan to learn how to make these perovskite materials. Back in Oxford, we managed to integrate them into what we were working on was solid-state cells, solid-state, at the time, dye-sensitized solar cells. So the device that Tom Miyasaka had developed, was based on a porous TiO2 anode, where the anode is sensitized, typically with the dye, but in the case of what he'd done, he'd used small nanocrystals of these perovskite materials, and then it's infiltrated with an electrolyte. So the big problem with this device was that the electrolyte dissolves the perovskite crystals, so the device lasted seconds. And I think this is probably one of the reasons why that work wasn't instantly followed. It looked like it was quite interesting, but just led to unstable cells. Whereas, in contrast, when you put the solid state, an organic hole conductor into the device, it was quite stable. So we had films that would be stable for 1,000 hours under sunlight, for instance, which was a massive step change. The big shock, if you like, or the first shock, was just our first batch of devices. They were already 6% efficiency. At the time, our solid-state dye-sensitized solar cells, we'd sort of hit a plateau at about 5%, and for 3 to 5 years, we couldn't get them any better. So this was already more efficient on the first attempt, and of course, it rapidly stepped up. So the first real surprise was that they worked instantly. Usually when trying a new material, if you can get 1% efficiency, you're pretty happy. Following on from that, with the way we were playing around with the way in which we process and crystallize the perovskite material, and what we were getting wasn't just small nanocrystals, but we were getting more of a polycrystalline material, very, very long-range crystalline order. And we had a suspicion that we were also getting charge conduction in the perovskite material. So we made some test cells, swapping out the porous TiO2, which was an electron conductor, with porous alumina, and actually we tested these cells to see how they worked under the sunlight. We weren't expecting highly functional solar cells because they had an insulator in place of one of the semiconductors, but surprisingly they actually worked better than the cells without TiO2, and we got a very big voltage step, an improvement in voltage. So this was the first real breakthrough, if you like, where we realized the perovskite material didn't just act as a light absorber, but it also acted as a charge conductor in the cell. Following on from that work, in close succession, we started investigating whether we really needed this porous alumina scaffold, and we made it thinner and thinner and thinner, and we got improved current, improved device efficiency at extracting charge. And when we looked at a section of these devices, they had a solid absorber layer of perovskite that was on top of a thin porous scaffold of alumina. So this told us already that the solid perovskite material can conduct charge out of the device. Now, that might not seem very surprising, but at the time, the paradigm was that you could either have a very expensive material that was a crystalline semiconductor, low defect density, and that would work as a solid absorber material. But if you went to cheap materials that were easy to process from solution at low temperature, they had a lot of electronic disorder, and they wouldn't work as a solid material. And to get them to work, you had to blend multiple materials, typically one material which would conduct electrons and one which would conduct holes, And in the case of the dye-sensitized solar cell, the absorber sandwiched between the two in a rather complex mesostructured or nanostructured device. And the way of thinking was that materials either fell into this category of high disordered but needed nanostructure, or low disorder and would work in a solid crystalline film. And the perovskites basically had the best of both worlds. They worked as a solid crystalline film, and they were very easy to process at low temperature. So they were clearly in a different category, if you like, a league of their own. Moving on from that, we demonstrated quite clearly that they could work as a solid thin film. And in fact, now the embodiment of a perovskite solar cell is that you have, on one side, you have a charge selective material, maybe an N-type organic material. You have the perovskite absorber, just a solid polycrystalline film between about a micron in thickness. And then you have a P-type material that might be an organic charge conductor or metal oxide, an electrode on the top. So it's a very simple sandwich structure device that we call a planar heterojunction or a double heterojunction. So since those first few publications, end of 2012, start of 2013, the research field of perovskite solar cells has absolutely exploded. So to put it into context, in 2012 there were 4 publications on perovskite solar cells. 2013 there were about 60. In last year, in 2017, there were about 2,500. This year, there's probably going to be 5,000 by the end of the year. So it is just sort of going up exponentially. Now, we were very, very fortunate to be there right at the beginning, and we've managed to stay in the front pack, ahead in certain aspects of the research. And that's really, in terms of sort of impact of research, obviously we've been lucky to be on this wave, riding this wave, and hopefully still riding this wave through to fruition. So the explosion of the field is the reason why we get so many citations for the work that we do.
What are the state-of-the-art perovskite materials at the moment?
So since the start, or at least since 2012 when the field took off, the efficiency of the small lab-based cells was just over 10%. So our first publication, we had 10.9% efficiency. Now that's increased to over 23% efficiency over the last 5 or 6 years. If we compare that to what's the efficiency of existing photovoltaics, silicon that's deployed today, mainstream multicrystalline silicon, is actually just under 23% efficiency. It's 22% efficiency. So perovskites have surpassed the efficiency of the most widespread deployable PV. So that puts them in a very strong position to look like a real contender for utility scale PV. But of course, perovskites carry a lot more risk than silicon. Silicon's been in the field for a long time. It's proven the stability is known, and we really come down to stability as a major component that we need to prove for the perovskite solar cells. So in terms of what's led to these improvements in efficiency, a lot of it's been device structure engineering and controlling the crystallization of the perovskite film. So making thick, high-quality perovskites. And that comes, in part, it comes from choosing the right components. So we've made a transition from methylammonium lead triiodide, which was the workhorse of the first generation of perovskites, through to mixed cation, mixed anion materials. So typically, a good quality perovskite might have formamidinium and cesium at the A cation site, lead at the metal site, and then a mixture of iodine and bromine at the halide site in the ABX3 crystal structure. There are many people exploring trying to put in multiple cations. There's, for instance, the addition of rubidium, even the addition of very small ions such as potassium and sodium. Actually, if you go smaller than cesium in the A site, the ion doesn't really fit into the perovskite structure. So many of these things that are published with sort of quadruple pentamal, six cations, they're probably not quite right. The perovskite's probably made of formamidinium and cesium, sometimes with methylammonium in there as well, and the other ions are really doing something else. They do have an impact. They're in the film. They may be going interstitially. They may be causing certain reactions on the surface of the crystal and the grain boundaries. So that's one component, has been tuning the composition. The other component has just been controlling the crystallization, working out good ways to process these perovskite materials. In parallel, in the perovskite absorber itself, in principle, is a pretty low defect density. There aren't that many defects, and the defects that exist aren't absolutely detrimental. They don't kill the performance, but they do limit the open circuit voltage. So one way to improve the voltage is to passivate the crystal. And in fact, passivation is really used in a very broad term because we don't really understand what's going on chemically, and there's lots of routes of post-processing of the films that improve, for instance, the radiative efficiency, the fraction of light re-emitted from the perovskite material. And that we term passivation, but we don't really know what's going on. It could just be recrystallization of the surface. There could be a whole host of things there. So understanding that surface chemistry, the exact chemistry at the grain boundaries and in the buried interface is really important. That's in part driven the performance improvements, but there's still massive scope to make it better, to go further. So we're currently at 23% efficiency as the record cells in labs. Actually, there's nothing stopping that pushing up towards 30% efficiency in a single junction cell. And that will happen by better control of the surface properties, in my view, of the perovskite absorber. Coupled with that, there's been a lot of tuning and optimization of the contact materials. But what is quite surprising is that we haven't had to develop new contact materials. We've just had to select materials that are already available, either from the organic electronics field or from the dye-sensitized solar cell or thin film PV field as well, where we've used metal oxides or organic semiconductors, and they seem to make very good electronic contact to the perovskite. But tuning the properties of those materials, for instance, doping of the contact materials, has all been part of getting the efficiency up and going up this ladder towards the Shockley quasar limit. But we've still got some way to go and quite a lot of headroom there.
What's the current progress of multi-junction perovskite devices?
I mentioned the efficiency of a perovskite solar cell was 23%, and that we could potentially get that up towards 30% efficiency. But that, to someone not familiar with photovoltaics, that seems like a pretty low number. It's like, why are we chucking away 2/3 of our power? But actually, there's fundamental limits to the conversion of sunlight to electricity, and they relate to the bandgap of the semiconductor that you absorb the light in. So if you have a very narrow bandgap material, this would mean that it would absorb all the light over the solar spectrum. You generate a very high current, but you wouldn't generate very much voltage. If you have a very wide bandgap semiconductor, you can generate a lot of voltage, but you're only absorbing a small fraction of the sunlight. So if a semiconductor had a bandgap of, say, 3 electron volts, you'd only absorb the UV part of the spectrum. And you want to absorb the UV, the visible, and the infrared. So this leads to a compromise where a bandgap for a single absorber material is the optimum bandgap, somewhere between 1 to 1.5 electron volts, and that gives you a maximum of somewhere around 30 to 32% efficiency. So that you think, well, that's it. Okay, we'll just work to make cells as efficient as we can. But actually, there is a way to make cells more efficient. And of course, if you look at the sort of the global efficiency chart that's published by NREL, there's solar cells which are 46, approaching 50% efficiency. And they do that by not just having a single absorber, but having multiple absorbers on top of each other. So you absorb different parts of the solar spectrum in different cells. And from the top cells that absorb the blue visible part of the spectrum, they'll generate a high voltage, and the cells behind will take out different sections of the solar spectrum, generating a smaller and smaller voltage. But by doing this, we can extract more energy from the sunlight. So this is a strategy for perovskites that we're starting to pursue, and it's looking very, very promising. So for instance, in probably the simplest embodiment is to take a perovskite cell and stick it on top of silicon, which is the existing PV material. And if we do that, we can improve the overall efficiency of that cell. So the present world record for perovskite on silicon is 27.3% efficiency, which is much higher than the 23% for a single junction perovskite cell, and it's even higher than the all-time world record for crystalline silicon using a very advanced technology, which is 26.7%. So this is the point at which perovskites start to take the lead. We've just passed all other possibilities with silicon, and now they can go forward. But it doesn't just stop at a tandem cell. And in fact, if we can estimate what sort of efficiency we can get if we put 3 layers on top of each other, then we could push it up towards 40% efficiency, which is feasible. And that could either be 2 perovskite layers on silicon or even an all perovskite multi-junction cell. So this is somewhere where I believe the field has to go and is going, and it's somewhere where I think there'll be a lot of excitement and interest over the next few years.
How can perovskite silicon multi-junction solar cells benefit from concentrator photovoltaics?
So as scientists, we always try to think about what's the next step for improvement. So going, for instance, from perovskite single junctions to multi-junctions. There's another way of improving efficiency, and that's to concentrate sunlight or increase the intensity of the sunlight. So you don't get more sun hitting the earth, but if you can concentrate the sunlight, what you do is you generate a much higher voltage out of the solar cell. In fact, these multi-junction cells that are 40% efficiency get boosted up to 50% efficiency by concentration. That's what's required. So the natural next step for perovskites would be concentration. I personally hadn't given this much consideration as a realistic prospect. So I'll have to give some credit to my postdocs, Ziping Wang and Qinqing Lin, who came to me one day to show me some of their results of intensity-dependent measurements of perovskite solar cells. And I thought this was very interesting. Scientifically, it's quite intriguing. But we ran some calculations and worked out that perovskite should really operate very well, up to many tens of thousands of solar intensity times concentration from the sunlight. But of course, the practical challenge is we've been struggling and making big improvements with the stability under one sun, but how can we make it stable now under 10 or 100 suns illumination? But actually, over the last year or so, I've convinced myself that this is a very good idea. So I'll try to convince you that maybe it's also quite a good idea. So in principle, we know fundamentally we can get higher efficiency out of concentrated sunlight. And in fact, what we've shown is with perovskite cells, this can be achieved with contemporary perovskite cells. They can be 21% efficiency under full sunlight, and we can raise that to approach 24% by concentrating the sunlight. They're the cells from our lab. So it can work. And in fact, we've seen many hundreds of hours stability under 10 suns illumination. So they're progressing well. And I wouldn't say stability is an absolute critical factor now. And in fact, if you think about a concentrating array, provided you can thermally sink the solar cell and have the heat radiated away, then in principle it can still operate at the same temperature as a flat plate technology would do, depending on your concentrating optics and everything like that. So what the opportunity here is, and it won't be with single junction perovskites, it'll be with very efficient multi-junction perovskites. The opportunity is not to go for, say, 1,000-fold concentration or 500-fold concentration that's required for present-day multi-junction cells. The reason why that's required is because they are just so expensive to make. These gallium arsenide and multi-layer gallium indium phosphide cells with germanium, they're made via epitaxial growth, and they cost tens of thousands of dollars a square meter. In contrast, perovskite's even cheaper than silicon to make, and yet we think we'll get to the same sort of efficiencies. So then we can think about deploying intermediate, or what's called low concentration factor, on the order of 10 to 30-fold concentration, and deliver a performance improvement and do that with very efficient cells. The other thing that's riding in favor of concentrated photovoltaics for perovskites is that the trends in deployment are moving towards solar tracking. So already presently deployed mainstream modules are put on a boom, so they've single axis tracking. Now that could be combined with a low concentrator factor solar concentrator. And there's even with existing technologies, they're put on 2-axis trackers in some higher radiance areas. So now the more power you get out of a module, the larger you offset the balance of systems cost. So as you move towards more powerful modules, we will move towards 2-axis tracking. It will become the norm at some point. At that point, you've got no additional cost in the tracking to do concentrated PV, and it's only then the optics and how you do that, which may be parabolic mirrors. So I think ultimately looking through, we will move to concentrated PV. It also gives another order of magnitude in the challenge of the stability issue, but we believe that's going to be surmountable. It will require new materials chemistry, new interface design and everything else, but it should be surmountable. So that could be the path for the next generation beyond multi-junction perovskite cells.
What's the current status of standard lifetime measurements for perovskite solar cells?
We can get extremely excited by efficiency and the remarkable performance of perovskites, the ease at which they can be processed. But of course, we're all aware that no solar technology is of any worth unless it can last in the field. Silicon PV modules today will last for 25 years. And that's proven, and it's known they'll last for 25 years because they have lasted for 25 years. So we're in a situation with these perovskite materials where they work very well, but we need to ensure that they're going to last for 25 years. And we don't have hindsight to know the tests we're doing to stress them are the right tests that will show up failures in the field. So this is really at the core of what we should be doing in research, looking within the community. So there is a slight discrepancy within the community between methodology for stressing the perovskite solar cells, how to report stability, what measurements really mean this stuff is quite stable, what measurements don't. And I had the pleasure of recently working with Peter Hacker from NREL and writing a paper on stability for perovskite solar cells, and I learned a lot in the process about what's been done in the past with existing thin film and silicon cells, and there's a lot we can learn from the existing industry. And also with my role in Oxford Photovoltaics, I'm exposed to that industrial side and industrial demand, and there really complying to industry norms is an absolutely essential component, but it's not all. That is something that has to be surpassed, and then we also need to go further and find if there are failures that exist that we don't know about. So that's where doing lots of more advanced tests, comparing laboratory tests to real on-sun testing is going to be an essential component going forward over the next few years. One thing that's presently lacking in the scientific community is being able to compare results of stability from one lab and stability from the other. There's a whole host of parameters. They include the spectrum of light that you're subjecting the cell to, the temperature, whether it's under load or open circuit, the atmosphere, whether they're encapsulated, how they're encapsulated, and a whole range of other parameters. The real critical thing is that these are reported, so it's very transparent as to exactly how a solar cell's been stressed, so you can make a comparison. But what would be better is if standards emerge that people adhere to, and we use them as the benchmark for, yes, this cell's more stable than that cell. And you can understand between laboratories whether chemistries improve things, not whether just the like-to-like comparison on the day was better or worse than the control. So this is something we look forward to seeing happening, and there's certainly on the European perspective, there's quite a lot of motivation between different European funded projects to try to come up with some suggestions of standard lab practices. But they will as closely as possible adhere to the International Electrotechnical Commission standards. On top of the stability stresses, actually just measuring a perovskite solar cell is different to a normal cell. We have some issue with mobile ions or ionic species in these materials. So again, there's effort to try to standardize the measurement technique. The key factor is that we have to either measure a stabilized or steady state power output, so you measure at a fixed voltage over time and take the current until it stops changing, and we call that a steady state power output measurement, or max power point track, where you track around the voltage until you stabilize the current. They're an essential component for quantifying efficiency in these solar cells.
What are the main factors affecting the manufacturing cost of perovskite modules? Can you talk about the current status of inkjet printing for perovskite modules?
Historically, there's been a lot of activity on printed solar cells, and this originated, or lots of the work was done on organic solar cells. Commercially, there's been a lot of work done on thin film SIGs. There was a company, NanoSolar, that raised many hundreds of millions to try to commercialize a printable SIGs technology. Mia Soleil, also, that ended up being taken over or bought by Hanergy, is selling a printable SIGs technology. And there's this dream, if you like, that printable, flexible PV should enable more than rigid base PV. One of the motivating factors is cost. The presumption is that reel-to-reel printing will be much less expensive than standard semiconductor processing. But there we really have to look at what's the cost of existing processing of silicon PV cells. And in fact, the cost of equipment and manufacturing has dropped by orders of magnitude over the last decade, an order of magnitude over the last decade. So now the capital infrastructure for a silicon line, say a gigawatt line, is only a small fraction of the overall cost if you cost it in cents per watt. It might be 2 to 4 cents per watt comes from the capital infrastructure when you depreciate it over 7 years. So looking at that, it's not obvious that you're going to get a cost advantage from reel-to-reel printing. There are many more challenges as well. One of them is that every process has to be coinciding in the line at the same rate, or you need longer routes to go through. So there are more challenges for the printing rather than batch processing. That means it's going to be a longer time till it gets to market. But it doesn't mean that ultimately there isn't an opportunity. And in fact, I strongly believe there is an opportunity for reel-to-reel printing, but there's lots of things we need to solve. One of the main opportunities is to have a laminatable foil, for instance, you can put in a building, or you can imagine with the electrification of cars, if you can have a laminate that gets laminated over all the car material that also produces very high power, that could be a fantastic way of offsetting the requirement to charge every so often. So there are applications, there's numerous applications for flexible, lightweight solar cells, but the key things we have to solve, one is the solvent system we use. Most of the academic work's still done with a mixture of DMF and DMSO, and that DMF is not compatible with high volume manufacturing. We also need to control the viscosity and do more work on advancing printing techniques such as inkjet printing, slot die coating or spray coating. These larger area coating techniques need to be developed. Most academic work's done on spin coating. That's not a methodology you'd use in manufacturing. One of the bits of work we did a few years ago in this line is moving away from DMF to acetonitrile. Now, acetonitrile is not a perfect solvent. You certainly wouldn't want to drink it, but it is allowed in manufacturing, and it's much better than DMF. There we found that if we bubbled methylamine through acetonitrile, we could then use it to solvate the organic salts. So we're now progressing with this work and looking at other solvent systems that could be more compatible with printing, but I think this is an approach that could lead to printable PV cells with very high quality of material. Another advantage, if we think about deposition methodologies, of course you can reel-to-reel via vapor. In fact, one of the leading, possibly the leading organic PV companies is doing vapor-deposited organic PV on reel-to-reel. So that's also an option for reel-to-reel. It also may be in batch processing. We need to understand, do we want to do vapor or solution processing? So these activities are still unsure. If you look in the academic literature, 95% of the work, maybe 99% of the papers, I haven't counted up, are on solution process perovskites. 1% are on vapor deposited. That isn't because solution process is much better, or certainly not fundamentally better than vapor deposited. It's simply there's more capital investment to get an evaporator and get it working than to buy a spin coater. A whole group of researchers, my group's 25 people, we have 3 spin coaters and they cost £5,000 each, compared to an evaporator may cost £200,000, and that will service 2 or 3 scientists. So the rate and cost of getting into the field for evaporation is high, but we will see more and more activity in this area. More and more groups are getting this capability, and we'll see growth in this area of research over the next few years. Moving towards multi-junction cells, I expect the vapor-deposited cells to advance more quickly than the solution process cells.
What's the current status of commercial perovskite modules?
As the research field advances, there's more and more of the developments are being patent protected, and this is also leading to the emergence of a number of companies trying to commercialize this. So, for instance, there's a company called Microquanta in China that's trying to produce thin film perovskite modules, as far as I'm aware, on glass. There's a company in Poland called Saul Technologies that's trying to do inkjet printed perovskites on flexible substrates. There's a few companies in the US, one called Hunt Energy Enterprises. We don't really know what they're doing. They're quite opaque. And there's another newly formed company called Swift Solar, and they're working on flexible multi-junction perovskite solar cells. The company closest to my heart is Oxford Photovoltaics. I'm a co-founder and CSO of that company, and there we're focusing on the perovskite on silicon technology, and we'd like to think of ourselves, we certainly think of ourselves as the first mover in this technology, and we're focusing on what we think is the most practical deployment strategy. So I'll show you an example. This looks, to all intents and purposes, like a silicon wafer, but it's actually a perovskite on silicon wafer. So this is made in the Oxford PV facility in Brandenburg, where we're scaling up to full size. So this, fortunately, when talking about silicon cells, is full size. So the scaling challenge isn't that hard. It's taken a lot of effort, but we can now make very efficient cells of this 6-inch wafer format, and that's full scale. So what we're doing now is trying to ramp up the volume towards pilot level manufacturing and then going beyond. One of the key targets in entering in essence, the silicon PV industry is to match the stability of silicon. There's no hiding away and offering a short lifetime product. For that, in Oxford PV, we've been laminating these cells and putting them into mini modules and stressing them through all the IEC environmental stress tests. And they're showing very good progress, not just to pass IEC, but to go well beyond, which is a requirement. But the strategy of Oxford PV is also to license and work with joint development partners who are existing in the silicon manufacturing chain, because that way the existing value chain can be capitalized upon, and instead of competing against the silicon industry, will actually enhance it. So that's something perovskites could do. They could literally be the next generation of silicon cells in the first instance. Ultimately, we see many deployment strategies. We see the flexible, we see the thin film, and especially the all-perovskite multi-junction coming through. But my prediction would certainly be that the perovskite on silicon will be the first products in the market. Then beyond that, we'll see the other technologies coming in.